So we've been exploring the idea of density operators for the previous 2 lectures. In short, the density operator is one way of representing quantum states, be they pure, be they mixed. So it represents both pure as well as mixed quantum states. And the general form of any density operator is that it can be written as a mixture of quantum states, where each quantum state is represented by an outer product of a ket with itself, weighted by some probability factors. K could be anything. K could go from 1, 2, 3 up to anything. So it's a mixture of quantum states. So this is an example of a general density matrix. For a pure quantum state, we know that it can be written as, I think I used the notation psi in my previous lectures, so I'll stick to that. This is a pure quantum state, just one ket with its bra. So you can represent a pure quantum state either by rho or just by the ket. This is the general form of a density operator or a quantum state. A pure state is a special form of a density operator in which this k is just 1. There is only one kind of probability, and that is 1. So this is our general density matrix. This is a pure quantum state. We also looked at what is meant by a separable state. Any state that can be written as rho A times rho B, and you can have i's of these and j's of these, sum up over i's and j's, and some factors, say p, I, j. This is an example of a separable state in which we can write a density operator for the first part of the composite system and a density operator for the second part of the bipartite system and form a tensor product of the two. So this is an example of a separable state. So all of this we already know. Examples. I can have a mixture of say, let's talk about single qubit. This is a pure quantum state, just get 0, and a superposition state. This on its own, if I just had this, I just had a ket, that would be pure state. But now I'm mixing two pure states together. And I have some proportion of this. Say I have P1 of this and I have P2 of this. Now P's and P1 and P2 are numbers. They're real numbers, positive numbers, they're probabilities, non-negative numbers. Now this density operator will be P1 times this outer product plus P2 times this outer product. Alright, this is absolutely different from ket 0 plus this ket. So it's not a sum of two kets, it's a sum of two density operators to form a new density operator, which is now a mixed state. So it's not a coherent superposition. This on its own, if I would just write this quantum state, this quantum state on its own can be written by, represented as a ket. It's a pure quantum state. And this is a coherent superposition between two basis states, ket 0 and ket 1. It's a coherent superposition. And of course I can write a density matrix corresponding to this pure quantum state. That's going to be ket psi bra psi. This will turn this state into a matrix. But this is a pure quantum state. And I can now so there's a huge difference between having a mixture of this state and this state, another state. So I can have some epsilon here, some 1 minus epsilon here, where epsilon is less than 1, and I need this because I want the trace to be 1. So this is a mixed state. This state is not the same as psi plus phi with 1 minus epsilon square root epsilon. This is not the same as this state. They're totally different states. So I'm not making a superposition of two pure quantum states, two kets. Rather, I am first making the density matrix and then mixing in the density matrices to get a new density matrix. This is the difference between a coherent and an incoherent mixture. So this is all that we've seen so far. Now what we would like to do, looking at a density operator, can we tell whether the state is separable or not? That's the question. So we want to come up with some test for entanglement. Suppose I have an entangled quantum state, pure state, which is a Bell state, phi plus, and I'm talking about 2 qubits. So this is 0, 1, 0, 0 plus 1, 1 under root 2, right? It's a Bell state. Bell state, which is 1 over under root 2, 0, 0 plus 1, 1. I can form the density matrix corresponding to this Bell state. This is the density matrix. Correct? Now, when I look at the density operator for this state, it's going to be a matrix. It's going to look like a matrix. And if I were to find out the matrix form of this is going to have a 1 here, 0, 0, 1. 0, 0, 0, 0. So this is the density operator for this particular state. And it's an entangled state. We all know that this on its own is an entangled state. And it's pure as well. But what if I have another state which is the maximally mixed state? And I'm talking about 2 qubits, so I need to divide by 4. So this is another example of a state. But now we know that this is not an entangled state, this is a maximally mixed state. Now what if I add some part of this and some part of the Bell state together? So I put in epsilon times this entangled state and 1 minus epsilon times this maximally mixed state to form a new state of 2 qubits. Now I know that this state is entangled on its own, this state is separable on its own. So when I intermix the two states, will the new state be entangled or not? That's the question. So in order to verify entanglement, we need to come up with some test for entanglement, some kind of witness for entanglement. So one possibility is that suppose I have a density operator rho. If I form the transpose of this density operator, will the new operator be also another density operator? Yes. Because the transpose of a Hermitian operator is again some other density operator whose trace is 1, it's a positive operator. So transposition is a positive map, as it is called in mathematics. It's a positive map, which means it takes a density operator, makes it into a new density operator, but the new thing is still a density operator. Okay? So if I have rho A, the density operator on the first qubit, cancel with the density operator on the second qubit. If my total density operator looked like this, which means that rho is separable, which means that the first qubit and the second qubit have identities of their own. And if I were to take a transpose of just one of the subsystems, this operation is called partial transpose. So I take the partial transpose of the composite density matrix, which means I take just the transpose of one of the two components of the bipartite system. Then my new object, if it remains a density matrix, then the initial rho could have been written in the separable form, which means that the initial rho would be unentangled. If partial transposition keeps the density matrix a legitimate density matrix, then it means that the density matrix is separable. Let me rephrase this. If the act of partial transposition keeps a density matrix a legitimate density matrix, then the density matrix is separable. Okay? So let me give you an example. So this, by the way, is called the positivity of the partial transpose test, the PPT test. Positivity of the partial transpose test. And you can pick up any density matrix, 2 qubits, and take its partial transpose and see whether the new matrix that it is made is a legitimate density matrix. And how can you tell whether it's a legitimate density matrix? Of course, you would have to have that rho is Hermitian. You need to know that the trace of rho remains 1, and you need to know that rho is a positive matrix, which really means you take any quantum state and sandwich rho in between, then this gives scalars which are non-negative. Rho is a positive matrix or a semi-definite positive matrix. Okay? This is something that we proved in the previous lecture. Now, let's look at our example over here. And if the density operator is positive, it means its eigenvalues are also positive. So if rho is positive or semi-definite positive, which is just a shorthand for this, then this implies that the eigenvalues of rho are also non-negative. And why is this true? This is true because this is the definition of a positive operator, where psi is any quantum state. Alright? Psi is any quantum state. This is how we define a positive operator. Alright? So let me backtrack a little bit. Let me show why rho is a positive density operator. I know that rho is given by some wk psi k, ket psi k, bra psi k, sum over rho k, right? Now I take its phi ket phi is some quantum state. Some quantum state. Excuse me. I think I need to change the pattern. Ket phi is any quantum state whatsoever, any legitimate quantum state. So this expectation value becomes phi psi k phi wk. Remember, these wk's are positive or non-negative because these are probabilities. Wk. This of course is the modulus square. Now is this always a non-negative number? Yes, and so is this. Therefore, this is always going to be a non-negative number. This is why rho is a positive operator or a semi-definite positive operator. Now this also means its eigenvalues are not only real, they are also positive. Why? Because if I were to take this state as an eigenvector of the density operator, eigenvectors will exist because it's a Hermitian operator. If I were to take this state as an eigenstate of rho, so this is true for any state, so it must also be true for an eigenstate of rho. So if, let's suppose I represent that eigenstate by ket rho m, अब्दुल्ला नीचे वाले फ्लोर पे ना
Yeah.
ठीक है. So what would be the result over here? Since this is an eigenstate, suppose that eigenvalue is rho m. So this answer will be rho m. But this must be positive. So this must also be positive. So a positive operator, like a density operator, must have positive eigenvalues as well. This also means that the density operator, like any Hermitian operator, can be spectrally decomposed. Spectral decomposition means that this operator can be written as a sum of outer products and formed from the eigenvectors weighted by the eigenvalues summed over m, right? Got it? So that's why we can always write a density operator in this fashion. Alright, so but no, थोड़ा सा ऊंचे इधर नहीं रहना फिर. Alright, so where were we? What we're trying to find out is this particular problem. Now I have this density operator rho equals 1 minus epsilon identity over 4. This on its own is mixed. It's mixed. Plus epsilon, the Bell state. All right, so now the question is whether this is entangled or not. So we want to apply the positivity of the partial transpose test. So one easy way of doing this is to first writing this in matrix form. It will be a 4 by 4 matrix. Identity over 4 has 1 over 4 on all the diagonal values. So 1 minus epsilon over 4, 1 minus epsilon over 4, 1 minus epsilon over 4, 1 minus epsilon over 4. plus I need to take into account these terms. So these will give me epsilon over 2 at the four corners. So I'll get an epsilon over 2 here plus an epsilon over 2 here, 0, 0, 0, 0, 0, 0, 0, 0, epsilon over 2, 0, 0, plus epsilon over 2. Right? So I just want to, this will become 4, 1 minus epsilon, 1 plus epsilon over 4, correct? ऐसे ही होगा ना? So this is my 4 by 4 matrix. Now I would like to take the partial transpose of this. Okay. So how do I take the partial transpose? Now if I look at how I ordered the and labeled these rows and columns, so let me do a labeling. This row corresponds to 0, 0, 0, 1, 1, 0, 1, 1. This corresponds to bra 0, 0, bra 0, 1, bra 1, 0, bra 1, 1. Now if I were to take the transpose of the second qubit, I can take the transpose of either the first qubit or the transpose of the second qubit. I can do either. Let's take the transpose of the second qubit. Now if you notice what's going on here is that in this top block, the first qubit is identically kept 0, but the second qubit is changing across the two rows. So if I were to take the transpose of the second qubit, I would have to adjust the elements of this block in such a manner that taking the transpose with respect to the second qubit would mean swapping these elements. Okay. Likewise, I would need to swap these elements. Likewise, I would need to swap these elements. These elements. If I were to take the transpose with respect to the first qubit, what I would do, I would swap these two blocks. Yes. Right. So if I were, so the labels decide. So look at this first top left block. In the top left block, all of these four elements have the same first qubit. The first qubit is 0, and so is here. So all of them belong to the, they have identical projection on the first qubit. Now if I were to transpose with respect to the second qubit, what that means, I would need to swap only those elements for which, if I were to take just this matrix, the transpose of this matrix would mean keeping the diagonals unchanged and swapping these two elements. Alright. So in this subspace, the top block subspace, it is covering both both kinds of states of the second qubit, 0 and 1, right? And so is here, so is here, so is here. So partial transposing the second qubit would mean that I have to swap these elements. All right. Now, if I were to do this swapping, the partial transposed density operator, let's see what that comes up as. You can also imagine this as the following. So if I had a density operator rho, this rho will have elements rho mn, correct? So this matrix is identified by a row and a column, mn. If I were to take rho t, the transpose, then this matrix, how will this matrix be formed? It will be formed by swapping m and n. So it will be the set of rho n and m. This is how we define a transpose. So now if you look at any of these terms, for example, this term here is given by all right. Each of these terms has a particular form. You take the density operator, this term represents this element. This term would represent this element here. Now, if I were to construct this, if I were to use this formula, swap m and n together. Now, there are two kinds of m's and n's. One is for the first qubit, the other is for the second qubit. So this really, each term really is now rho m alpha n beta. So now I have 4 indices identifying each element, if I were to talk about 2 qubits, where m and n are Latin letters representing the first qubit, and alpha and beta are my Greek letters representing the second qubit. So each row is made up of these elements, and partially transposing with respect to the second qubit would really mean that I am keeping the English letters unchanged, or the Latin letters unchanged, and I'm swapping alpha with beta. M, beta, and alpha. This is what partially transposing with respect to the second qubit means. Now, if I would use this algorithm, which is now defining my partial transpose, this is what's going to happen. You get it? So just go home. I know it's very close to iftar time, but if I were to use this formula for defining the partial transpose, in effect this is going to interchange what I've connect the two elements that I've connected with these green lines. And when I were to do this partial transpose, the new matrix that is formed, I still don't know whether it's a legitimate density matrix or not. I need to find that out. But the new matrix that is formed is the following. So I'm just for convenience breaking this down into 4 blocks. 1 plus epsilon over 4, 0, 0, 1 minus epsilon over 4. Now 0, epsilon over 2, 0, 0, 0, epsilon over 2. This is 0, 0. And then, is this a plus here, right? ये plus है ना? 1 minus. 1 minus, right? Then I have 1 minus epsilon over 4, 1 plus epsilon over 4. So this new matrix is formed by taking the partial transpose of one of the sub-matrices. If my original density matrix were separable, that is, it were indeed a tensor product of two standalone density operators, then partial transpose should have done nothing. Which means that if I were to take the eigenvalues of this matrix, they would all be positives. Let's see if they are positive. So it will have 4 eigenvalues. So 2 of the eigenvalues are stark clear. 2 of the eigenvalues are, one of them is this, the other one is this. But you need to find the eigenvalues corresponding to this block here. Right? So this is K, one of the eigenvalues. So if I were to take a spectrum of this, which means a set of eigenvalues, one of them is 1 plus epsilon over 4, this one. The other one is also 1 plus epsilon over 4, because they are the only elements in their row and column. They don't have any overlap with anything else. And now this block is formed. Any guess what the eigenvalues of this block would be? Can you please determine the eigenvalues of this submatrix? इन चारों की? नहीं, you just need to focus on this block here. So, what are the eigenvalues of this operator, sigma x? One and minus one. So the eigenvalues of all the 3 Pauli operators are 1 and minus 1. Sigma z has 1 minus 1, sigma y has 1 minus 1, sigma. So if you look at this block matrix, it has a sigma x in it with an epsilon by 2. So one of the eigenvalues will be epsilon over 2, the other will be minus epsilon over 2. But it also has these diagonal elements. And the diagonal elements, if you just had the diagonal elements, the eigenvalues will just be the diagonal entries. So one of the eigenvalues will be 1 minus epsilon over 4 plus epsilon over 2. Which is going to be 1 plus epsilon over 4, and the other eigenvalue would be 1 minus epsilon over 4 minus epsilon over 2, which will be 1 minus 3 epsilon over 4. So the eigenvalues are 1 plus epsilon over 4 thrice, 3 times, and 1 minus 3 epsilon over 4 once. So these are the 4 eigenvalues of the partial transposed operator. We still don't know whether it's a legitimate density matrix or not. So if epsilon is always, it has to be in this range, right? Because our initial density operator here, if it were to be a legitimate density matrix, then epsilon must be constrained in that fashion. Correct? Now, under what condition are all 4 eigenvalues positive? When is this a legitimate density matrix? When all 4 of these eigenvalues are positive. Now, this is always positive, always positive, always positive. But what about this? This can be positive or negative. And it's positive when epsilon is bigger than 1/3. So this is our threshold. So if our epsilon is bigger or equal to 1 by 3, then one of the eigenvalues is turning out to be negative. Which means that my initial density matrix, in which I had presupposed it were written as a tensor product of two standalone density matrices is incorrect, which means that the state is entangled. Let me rephrase. If one of the eigenvalues turns out to be negative of this matrix, this means that the act of partial transposition renders the operator into a non-legitimate density matrix, which means that my initial separable decomposition was incorrect, because partial transposition should preserve a density matrix. This means that my initial supposition of writing the state as a tensor product of two density matrices, that is a separable state, was incorrect, which means that my initial state was entangled, non-separable. So this is the positivity of the partial transpose test. If my epsilon, this thing, is bigger than 1 by 3, if I have more than 30% of this, 33% of this, less than 66% of this, my state will be entangled. Otherwise, it's going to be separable. It will have a separable description. Now, it's not always easy to write a separable description of a state, but at least this test tells us whether the density operator initially is separable or entangled. Now, the last thing that I would like to mention about density operators is the idea of a reduced density operator. Now, to finish off our discussion of, suppose I input a Bell state into two channels, and I forget about one of the qubits, and I just did a measurement over here. So here is my measurement apparatus, a beam splitter perhaps, and two detectors. Now, even if this is a pure quantum state, remember this is looking like a pure quantum state. I am inputting a ket, even though it's an entangled ket. I am inputting a pure quantum state, which is entangled as well into this two-channel system, but I'm ignoring one. So only Alice is making a measurement on her qubit, and she has nothing to do with what Bob is doing. So this is Alice, this is Bob. Now, what does Alice see? What kind of state does she see? Now, we know that for an entangled state, the two qubits do not have an identity. It's hard, in fact impossible, to tell what the state of the first qubit is. So, if she were to perform a measurement, she will get different outcomes, ket 0, ket 1, sometimes get 0, ket 1, ket 0. So, she does repeated measurements, she has a continuous stream of input Bell states. And she's just looking at her own qubit, oblivious of what's happening with Bob. Okay? Now, what kind of state does she see? Her statistical outcomes have to be describable by some quantum state. That's how we define a quantum state. But it turns out that that quantum state is not pure, it's mixed. So in order to describe what kind of state she gets, we'll have to use the concept of a density operator. In fact, the density operator of just her side of the story. And this is called a reduced density operator. So if I were to take this entire input quantum state, which is 2-qubit state, which is bipartite. Bipartite is my name for a 2-qubit state. Bipartite, which has two parts, or a composite state. If I have a bipartite state, rho, and I represent it by AB, which is the density operator for the 2 qubits. In this case, the density operator is going to be ket phi, bra phi, right? And its form is going to be this thing, right? This is my rho AB, my initial density matrix for the bipartite system. And generally books don't cover this with so much depth and so slowly, they just go over this, but I really think it's important. It's conceptual. Now if Alice just looks at her system, she will have just access to her reduced density operator. Let's call it rho A. Okay? So this is called a reduced density operator. And this reduced density operator is found out from having some operation on the big density operator. Now if you have a density operator, it's of course an operator. It has certain dimensions. Now if you were to take the trace of this density operator, what is the result? Is it a number or another operator? It's a scalar. It's a number. So the act of tracing reduces the dimensionality. Now you don't want to do the trace all the way, because after all you want a density operator here. So you have a four-dimensional system, and from that four-dimensional system you want to get it into a two-dimensional system. Right? From 2 qubits you want to get into 1 qubit. So you don't do a trace all the way, you do a partial trace. And that is represented by trace, and you want to trace over B. Trace over B, wash over B, you ignore B, average over B. You want to do a partial trace over B. Put a small b here. You want a partial trace over B to find the reduced density matrix of A. Okay? That's what you want to do. This is how we symbolize this operation of partial traces. So reduced density operator is obtained from partial traces. And how do we do that? So now the reduced density operator, so how do we define this? The reduced density operator of A, its ith row, jth column, the term in the ith row and jth column is formed by row AB Now row AB is identified by 4 elements, correct? So this is identified by I, alpha, J, alpha, sum over alpha. Now let me write this in a different fashion so that it's easy to understand. Row A so it has a row and a column ij is defined by row AB. Now row AB is defined by something on the first qubit, something on the second qubit. So the ket has 2 indices for the first and the second qubit, and the bra also has 2 indices for the first and the second qubit, right? So this will be I, but for the second qubit, alpha. J, ket J alpha. Remember, this is the first qubit, this is the second qubit in the dual space. The first qubit, the second qubit, sum over all alpha. For example, so let's make concrete sense of this. Row A, let me write down row A. Row A, this is my row A, reduced density operator. It will have 4 elements, correct? One is row 0, 0, row 0, 1, row 1, 0, row 1, 1. So these are elements. So when I put subscript with row, it means elements of row, where row ij means bra I row जी अभी ट्रांसपोज नहीं लिया कुछ. So this is my reduced density operator. Of course it will have 4 elements in this form, and this is the indexing of these elements. Now what is my row 0, 0? 0, 0 will mean row AB 0, 0. So I keep the first qubits fixed in the row and the column, and the second qubits I take the running sum. Correct? So this is just one implementation of this formula. If I want to find the 0th row, 0th column element of row A, which is here, which lies here, I take the big matrix and find, so I fix 0 and 0 for the first qubit, and I take the running sum over this second qubit. 0. First I get 0, and I have identically 0 here and here, and then I have identically 1 here and 1 here. This is just this formula, alpha, alpha. Okay. Similarly, row A 0, 1. Now I am turning my attention to this term. How do I get this term? I take row AB, I fix 0 and 1, and for the second qubit I take the running sum zero, 1 over all the possible indices. Okay, and so on. So what does this mean? If I were to write the big row AB first, let's write the big row AB. Row 0, 0, 0, 0, row 0, 0, 0, 1, row 0, 0, 1, 0, row 0, 0, 1, 1. This is the first row. Right? Then the second row, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Row 1, 0, 0, 0, row 1, 0, 0, 1, row 1, 0, 1, 0, row 1, 0, 1, 1, row 1, 1, 0, 0, row 1, 1, 0, 1, row 1, 1, 0. These are the elements in the big matrix row AB. So how do I get the first term? How do I get this term? What terms do I need to add? I need to add row AB 0, 0 with row AB 0, 1, 0, 1. I need to add these terms together. How do I get this term? The 0, 1 term. So the first term will come from the addition of these terms. The second term will come from the addition of 0, 0, 1, 0, which is this term, plus 0, 1, 1, 1, which is this term. So the top right term will come from the addition of these terms. Alright. Likewise, row 1, 0. So 1, 0, 1, 0. So look at the first and the third position, 1, 0, first and third position, and do a running sum over the second and the fourth. 0 here, 1 here. So I add these terms. This sum will come here. Finally, the sum of these terms will come here. So in this fashion, I will have washed away the second qubit. Correct? Or just obliterated its effect or averaged out its effect. And it turns out it is also making sense if you look at this density matrix closely. So this is the 0, 0, this is 0, 1. So this row is indexed by 1, 0, 1, 1. Now if you look at these two rows here, I can put a bra here as well, 0, 0, 0, 1. Now I am adding these two terms. Both of these terms have the same first indices, right? First indices are the same. Both of these rows have the same first indices. And you're taking a trace of the second qubit. So you want to somehow average out the effect of the second qubit. These terms are different in their second qubit. This is 0 here and this is a 1 here. So you want to add them up. You want to average over the second qubit. So you want to take those terms which have different indices for the second qubit. And this is how you form the partial transpose, the partial trace over the second qubit. If I were to take the partial trace of the first qubit, you can imagine what you're going to do is what you will do is you will take the sum of this term with this term. Because now you want to keep the second qubit the same and you want to average over the first qubit, which are different here, 0 and 1. So you want to add this with this. And then you want to add this with this. And then you would like to add this with this. And then you would like to add this with this. So you would just like to add the top left block to the bottom right block if you wanted to take out a partial trace with respect to the first qubit. You want to take a partial trace with the second qubit, as we've done. This is what you do. Add these two, add these two, add these two, add these two, and write the result over here. Now if I were to look at my entangled state, this state over here, which is rho AB, is my entangled state, pure, perfectly pure. Half, 0, 0, half, 0, 0, 0, 0, 0, 0, 0, 0, half, 0, 0, half. If I were to do the partial trace over the second qubit, which means I have to add these two terms, these two terms, these two terms, and these two terms. When I add these two terms, I get a half over here, 0 over here, 0 over here, and a half over here. So what is this looking like? Just looking like identity. And this is where the real entanglement comes to full bloom. Maximally mixed, maximally disordered state. Alice on her own is looking at a state that is perfectly random. Perfectly random. Sometimes she's getting cat 0 as the output, sometimes she's getting cat 1 as the output. But initially, the 2-qubit state that entered the system was perfectly aligned or perfect. It was pure. It was not random at all. It was a pure quantum state. Its purity was 1. But when just a subsystem is observed, the purity turns out to be 0. It's actually 0. It's maximally mixed. Since one of the reduced density operators here is maximally mixed, you cannot have anything more mixed than the density operator. It's totally random. In fact, if you talk in terms of entropy and look at entropy, its entropy is maximum. Log of 2, maximum entropy, which is totally disordered state. A pure quantum state has entropy 0. It's pure. You know what the outcome is going to be. So a pure state is something whose outcome you know for certainty. Right? So there is really no information contained in the pure state. Its purity is maximum, its entropy is 0, its information content is 0. Something you're certain about, if it were to reveal to you, it will not add to your body of knowledge. The sun rises in the east, it's certainty. This statement carries no information. Okay, its entropy is 0. It's pure, it's pristine. But something here, you start off with an entangled, pure entangled state, and Alice is observing her qubit to be totally random. Maximal entropy, maximum disorder, maximally mixed. And since this is reduced density operator is maximally mixed, therefore the input state is maximally entangled. This is how you define maximum entanglement. The degree of entanglement in this state is maximal. And there are degrees of measures of entanglement as well. How entangled is the state? Alright, so you can have different measures of entanglement like concurrence and so on. If Bob were to do a measurement ignoring Alice, he would also get a maximally mixed state. So this is the concept of the reduced density operator. So now in these 3 lectures, and it's taken longer than I had expected, we've gone through different aspects of the density operator. In real systems, you do not have pure quantum states, because these pure quantum states will decohere. They will become randomized over time. You really have to deal with mixed states. In the next lecture, what I'm going to do, I'm going to start some more, I'm going to talk about classical information in the next lecture. Because then I would like to talk about quantum information and quantum cryptography. But one lecture on classical information. What is information? What is entropy? What is mutual information, conditional entropy, and so on. Just one lecture on classical information that you would find in a classical computer science or classical electrical engineering course. Okay? And then we will make the connections to quantum communication. Shukriya. And do work hard on your, you need